So this is the algorithm that we were discussing about. What we do is input the instances. We have this X bar. What is the input instances to the network? And we compute the output. If you remember, how did we compute the output? We got to know that whatever the function that we are using, right? Output of W, comma, X. So we performed a sigmoid function or any of the function. Suppose here we did a signum function in our example. Of this output, we got the final output value. Yes. So this was our output. So with the input instances and the weights that we consider, we try to apply the activation function and we get the output. That is what we perform with respect to the network. Propagate the error backwards through the network. So we also know how did we propagate from the output to the input. Yes, back propagation, the way in which we did the back propagation algorithm, we just saw that, right? So it's a similar idea of it. Okay, for each network output until K, calculate its error term delta K. If you remember, where did we encounter delta K? Where did we get delta K from? Where did we get delta K from?
The output.
Exactly. So we got this delta K from our training rule with respect to output weights. So delta K is equal to, okay, I wrote it as OJ. If you remember, OJ into 1 minus of OJ into TJ minus OJ, right? But here we are considering K as our output. So we'll be writing, instead of J, we will write everything as K. So this is what we do. Delta K, we got the output value of it. For each network output, you can see here, for each network output, which means we are calculating the training rule for the output weights. So we have already done that. So when we go, okay. So after that, for each hidden network, what was the value that we got? If you remember, in the previous derivation, we got some value, right? Which was OJ into 1 minus of OJ, summation of K is equal to downstream with respect to the number of J values, W, JK into any of the other terms that we got? Into delta K, because this is for the hidden neuron, but we again have the output neuron with respect to ED. So we calculated, this was the term. This term becomes delta K. So the delta K is there. This is WJK. WJK value we have, and OJ into delta OJ is one value of the neuron, right? So we take all of these three values, that becomes our hidden unit H. So the value of it is the same. We get the value of it. And the final is we update the weights. We clear it. So we update the weights using delta W, that is WJI is equal to, so W new is equal to W old plus delta WJI. So delta WJI is basically, we already know this, the learning rate into delta J into XJI, the value of the input into delta J and the learning rate. So we finally update it using this update rule. Yes? Do you have any doubts here? Three main important steps that we perform with while we are performing the backtracking to identify the errors. The first is the training rule with respect to the output unit, the training rule with respect to the hidden unit. The final is the weight updates to each and every weight we perform using the weight new is equal to weight old plus delta, the change in the weights. The change in the weights we already know, this is the training rule for change in the weights, which is learning rate, into delta J. I hope you know what delta J is, into xji. Delta J is basically each and every neuron wherever I consider, I'll be applying that output, whatever the output weights that I get, I'll be applying it with delta J. It's similar to delta K into xji. So this is about your algorithm with respect to back propagation. I hope I've made this clear. Can we continue? Do you have any doubts? If you have any doubts, you can ask me, else I will continue forward.
Mom, can you again tell me about the delta K, mom? I didn't get what is it, mom?
Delta K, okay. So we already know how, okay, to begin with delta K, basically we are going to take the case 1 example where we are going to calculate the training rule for the output neuron. So when I tell the output neuron, I have this is my hidden, okay, sorry, this is my output layer. 1 second. So I have my output neuron and I'm going to get the value of it. To get the value of it, we did a derivation in the previous class, which is ED with respect to OJ, and this was net J, right? We perform the operation from ED, so delta ED with respect to delta OJ, that is this term, first block, and from here to here was the second term, into delta OJ divided by delta net J, right? So this basically gave me the equation of minus Tj minus Oj. We did a partial derivative of that equation, right? If you remember, Rahul?
Yes, mom.
So this is the partial derivative of that equation. So when I perform the partial derivative of the equation of ED was 1 by 2 summation of k is equal to 1 to n t minus of O the whole square. When I take a partial derivative, 2x into, it's going to be 2, 1 t minus of O into delta x value was minus 1, right? So this 2 and this 2 gets cancelled because it's 1 by 2, right? This 2 and this 2 gets cancelled. I get minus of t minus of O. So it's Tj minus of Oj. This was the first parameter. The second parameter for that is when I have to get the value of one particular neuron, I already know the equation or the derivation of that, which is Oj into 1 minus of Oj. The output of that particular neuron with 1 minus the output of that neuron. So basically I'll be writing it as Oj into 1 minus of Oj. Rather than specifying everything, we told that until this particular term, we will write it as delta K. So it's going to be minus delta K is the value that we will be applying it for the output neuron, right? This was our output neuron. So I'll be writing it as delta K is equal to, you can see OK minus 1 minus of OK is the value of the neuron that I'll be getting. Along with that, I have to get this value. The value of this was Tj minus of Oj, which is Tk minus of OK. When I consider K is equal to, or J is equal to K, when I'm substituting the value of that, I will get this equation, which is delta K. So basically it was minus delta K for the output neuron that we take out. So this is for the output unit. For the next weight was for the hidden unit. The hidden unit basically again so are you clear about this, Rahul? How did I get delta K? Are you clear about this?
Yes, mom.
Any doubts? How did you, anywhere, if you have anything here? See, because you can correlate this directly to the structure like this. So when I tell the output neuron, this is what my output neuron is. and I know the value of this is OJ or OK. The value of this is ED. The value of this is net J, or I can directly write when I want to get the value of one particular neuron, the value of it is with respect to the output, it's OK minus 1 minus of OK. Then I have to get this difference. When I have to get this difference is basically the partial derivative of ED divided by the partial derivative of that particular output value, right? So when I take the partial derivative of this, I will get this value. Rather than writing every time like this, I will assign it to delta K. That's it. One simple term for the output neuron. Clear? Any doubts here? Any doubts here? And when I consider the hidden neurons, again, it is very easy for us to identify. When I tell the hidden neurons, I'll have one neuron. This is my output. Before that is what my hidden neuron is. Until here, to my output, I already know the value of this is delta K, because just now I calculated it. So I have to go one step previous to it, and the weights of it is delta Kj, and maybe this will be the value of this basically is going to be Oj, the output of this. So the neuron, when I consider it, is Oj into 1 minus of Oj. This particular neuron, when I have to calculate, I know that the derivation of that is Oj minus 1 minus of Oj. So basically it is going to be, when I have to calculate for the neuron, the multiplication of all of these three, delta K into Wjk into Oj minus 1 minus of Oj. The value of that is what I've written it over here, which is the weight value of it, weight into delta K, this delta K into weight into Oj minus 1 minus of Oj. That is, they have written it as OH because it's the hidden. They are representing it as H. So I'm writing it as delta H. So this will become entirely my delta H value. I'm just assigning the value. Every time when I have to calculate for each and every neuron, I need not require to calculate, I need not write this equation. So I'll just write it simply representing it delta H and delta K. Delta K is the output unit, the weight vectors for the output unit. Delta H is the weight or the training rule for the hidden unit or the hidden neuron. And finally, I'll be updating the weight. So these are the three important steps that we perform when we are applying the back propagation. Any doubts here?
No.
Okay. Fine. This is what your derivation is. I've written down for your understanding. There are few things which I've highlighted, so it will be helpful for you to understand, okay, what is net J or what is Wij, what is Oj, the values of it. It's easy for us for understanding. So I've written everything in steps for you, so it will be easy. So this is what I was telling, the training rule for the hidden unit weight. This is what we get, the value of it, which we are downstreaming for each and every value. So we get it. Okay, so today's topic will be going ahead with clustering k-means. Okay, k-means clustering algorithm. It is one of the unsupervised learning algorithm. K-means clustering is an unsupervised learning method where I will consider that I have the inputs. Okay, let me differentiate it two colors. Okay, so I have certain data points. We already know that how does our data points vary, or when we are clustering, right? When I tell clustering, it's a supervised learning algorithm. You do not have a label associated with it. We just give only the data points to it based on the value of the data points, based on the similarities between the data points, it starts to cluster. Very important point is identifying the similarities between the data points and grouping them together forms clustering. Okay, suppose let I consider I have, these are the objects that I have. Okay, these are the data points that I have. X is equal to x1, x2, so on up to xm, where each value of it lies between xi1, xi2, so on up to xin. And I have some k clusters. Okay, these are the clusters that I want to come up with. Okay, so when I tell about this example now, let me give you an example over here with respect to your class. Okay, I have a certain people where I have to categorize. Okay, I don't know your names. So right now, since we are not on the virtual mode of it, we are just on the online. Okay, let me consider that all of you right now, I do not know your names and I do not know how you look. Okay, but I really have to categorize you into two different groups. Okay, boys versus girls. So based on the similarities between each and every data point whenever I consider, I identify whether that will belong to, and I start grouping them into two different categories. Okay. So, but when I'm going to categorize that, what I do here is initially I'll be identifying something called as, just give me 1 minute. So when I tell I have to categorize the students into two different groups, right? I initially start with some data point, a random data point. So which means that whenever I have to pass some information to the class, we have a concept called as class representatives, right? So which means that they are the direct point of contact to us. So whatever we have to deliberate, whatever we have to give information to is being passed to the class representative. From the class representative, it passes on to the other data points. A similar analogy here. Basically what we consider is we consider something called as centroid or the cluster centers. Okay, centroid or cluster centers, which helps us to group similar data points into one cluster. Okay, how does it do? I will let you know. But basically what it does is it identifies, first thing is identifying this k clusters. See, what are k clusters? Remember Gaussian points? We had discussed something with the EM algorithm, estimation maximization algorithm, EN algorithm. We had discussed a concept called as Gaussians, which means that if you remember, there was a bell curve that we discussed, and any data point, okay, given to us, we calculated the mu of it and its standard deviation, the way in which it was distributed. If we get to know the mu and standard deviation of the data point, we can classify them into categories, right? So this was the thing that we actually learned from the EM algorithm. See, a similar thing that we are applying over here. First, what we do is we identify a data point. Okay, suppose that I consider this is my first data point. So now I'm considering this is my cluster center. Okay, let me consider this is C1. Okay, and for the other one, I will consider this is my cluster center called as C2. Now what I do is I have to identify the similarities between the objects. Yes, along with that, I have to find out, first thing I have to find out the distances between the points. The points that are very closer to that, it will group that into one cluster. Example is, now from C1, I will consider this point, okay? I will identify the Euclidean distance. We know what Euclidean distance is, right? So basically it is x2 minus of x1, y2 minus y1, square root of is what our Euclidean distance is. Okay, so I'll be identifying the first Euclidean distance. That's my first point. Again, I will identify the second point, again third point, fourth point, fifth point, sixth, seventh. I will be calculating the Euclidean distances that are closer to that particular centroid. Okay, so when I identify this, I will be forming them in the form of groups. I will cluster them in the form of groups based on something called similarities as well as the distances between the data points. So there are very important key points to be noted with k-means. K-means basically tells us how many clusters you want to classify. Okay, this k is again something very important. There's a lot of research still going ahead with identifying the k value, identifying the k cluster values for the given data set, because each and every data set, this value actually varies. Okay, so identifying k is the first task. How many clusters you want to identify? When I tell how many clusters, right, if initially I start with first cluster, okay, so this is the first point that I'm going to discuss again. Okay, k is the number of clusters that I want. Okay, so the number of clusters, if suppose I will consider if k is equal to 1, I have many data points in this. I have many data points. So I'll consider this is my cluster center. This is my C1 now. Okay, cluster center is basically dependent on the number of clusters you have. So when I tell k is equal to 1, I'll have only one single cluster center. Now what I'll do, I will identify the distances between them. I will identify the distances between them. Okay, and I will take the average of all of these values because I want to cluster them. When I have to cluster them, I will take the average of it, or I will take the mean value of it. Okay, when I take the mean value and I have to represent it in certain terms, okay, that term we normally call it to be as within cluster sum of squares, which is nothing but, and I take the mean value of it, this mean value basically we consider it as within cluster sum of squares, WCSS. What does WCSS mean? I'm repeating it again. Within cluster sum of squares means that I am going to calculate the average or the Euclidean distances. Euclidean distances itself is basically, we know Euclidean distance from one point to the other point, I will calculate what is the value of it. So this is the value that I've calculated for the first point. I calculate for the all remaining points in the given data set, okay, and I take the average of all of those values. The average of all of those values is defined to be as within cluster sum of squares, because this is one cluster. This is one cluster.